I wanted to take a minute and go through a couple of these problems with you guys since I didn't put any in the video. I know that this might be a little bit weird, but we'll run through this one real quick. Number 2 says a wave on a wire with a wavelength of 0.3 meters is traveling down a 300-meter wire whose total mass is 15 kilograms. Okay, so we got a little bit of information there that we need to separate out. Okay, lambda is 0.3 meters. Lambda is wavelength, and of course, this is describing a wave. Okay, it's traveling down a 300-meter wire. That is describing not a wave, that's describing a distance of the medium. So x is 300 meters, and in fact really that's a length. So instead of using x, I'm going to use L. Okay, the length of this wire is 300 meters. It's got a mass equal to 15 kilograms. Okay. If the wire is under 1,000 newtons of tension force is 1,000 newtons. Find the speed and frequency of the wave. Well, there's two equations for the velocity of a wave. There's the standard one, which we use a lot, wavelength times frequency. But for a wave on a wire or a string or whatever, there's this other equation, the square root of the tension force divided by what I call linear density, or mass per unit length. Now, this equation is similar to like the frequency of a spring. You've got what's causing it to happen, the force in the spring or the force in the string, and then you've got divided by what's opposing it, or the inertia, and this is basically the linear inertia or the mass per unit length of what it is. So this equation does actually kind of make sense if we just think about it from the Newtonian perspective of force, mass, acceleration, speed. Alright, so I'm going to start with this equation because I don't know frequency, but I do know the tension, I do know the mass, I do know the length. So I have V equals the square root of 1,000 divided by, and put this one in parentheses because this is the denominator, mass, 15 kilograms per unit length, 300 meters. Okay. Now this is going to start as a big number, but then you square root it. So 1,000 divided by, and I'm putting in a parenthesis, 15 divided by 300. Okay. And I get that, and it's like 20,000. But then I square root that, and it's 141 meters per second, which is still fairly quick, 141.4 meters per second, but it's not near 20,000. Okay, now the last part on this is frequency. Well, now I can sub that back into this equation, and I can say 141.4 meters per second is equal to 0.3 times f. Divide both sides by 0.3, and we get a frequency of about 471 hertz. Okay, so this one is just a matter of using both equations to help you find velocity. 3 is similar. 4 is a little bit more challenging. Okay, and it's because I don't tell you mass, I tell you density. I don't tell you everything you need straight up. You actually have to do a little bit of math with this. Now, a rope or a cable is essentially a cylinder, right? And so I told you the diameter of it, and I told you the length or the height of it, and you're supposed to find the speed. Well, you're going to use this equation, V equals the square root of Ft divided by mass per unit length. Now, the problem is you don't know mass. What you know is you know density. Okay, density is rho, which I can't ever draw right. It's a Greek letter, looks like a lowercase p. Okay, and density equals mass times, or not mass times volume, mass divided by volume. Okay, so I gave you its density. If you take the density times the volume, you end up with mass. And then you're going to end up dividing that by length. Well, I want to show you something. The volume of a cylinder, this thing, is volume is base times height, right? V equals base times height. Well, the base is the circle, so its base is pi times the radius squared, and its height is however long it is, L. Okay, so what I have over here is the density times pi times the radius squared. Now this is the diameter and it's in centimeters. So if I take 1.5 and divide it by 2 and then move the decimal place to the left 2 places, I get 0.0075 meters squared. Okay, and then that's going to give me the mass, but I don't necessarily want mass. Oh, and then I'd have to multiply that by the length, right? And that's mass, but I don't want mass, I want mass per unit length, so I'm going to divide this by length. Well, that means that L goes away. So really all I have to do is take the density, 7,800, and then multiply it by pi r squared, and I'll actually have the mass per unit length. Okay. The tension in the cable is pretty high, the velocity is there. Okay. Anyways, I guess this is actually for part B. Part A, you're going to use a different equation, right? You know the velocity at 16 seconds for it to get there and back again. So 620 one way plus another 620 back divided by 16 gets you the velocity, and then you can use this equation down here to find tension. Okay. Let me know if there's any troubles with that. Otherwise, I will take those worksheets.